Right, imagine this for a second. Albert Pujols, maybe the greatest hitter of his generation.
Absolutely dominant, yes, a real force.
Steps up to the plate, everyone's bracing for a home run. But then, the pitcher, Jenny Finch, she's throwing underhand softball style.
Ah, completely different discipline, different mechanics, different visual cues.
And Pujols just, well, he swings and misses, strikes out. It actually happened.
It did. It's a brilliant example, isn't it?
Yeah.
Really highlights how specific skills are.
Or, here's another thought. Elite athletes, right? We hear about the 10,000 hours, but what if some reach the top with, say, only 600 hours of practice?
That's another key piece of the puzzle, definitely. It challenges that whole narrative.
Welcome to the deep dive. This is where we take stacks of sources, research papers, articles, expert insights, and really get stuck in pulling out the surprising facts and hopefully some genuinely valuable understanding for you.
Giving you that shortcut to being really well informed on complex topics.
Exactly. And today, we are diving into one of the biggest questions in sport, aren't we? What actually makes an extraordinary athlete?
Is it sheer hard graft? Hours and hours on the training ground.
Or is it more about winning the genetic lottery, having the right body from the start? Or maybe it's some complicated mix of both.
That's what we're aiming to unpack today, peeling back those layers.
And joining me to guide us through this really fascinating, sometimes confusing world of sports science is Professor Mo Imam. He's brilliant at pulling together information from different fields and helping us see the connections.
Thank you. It's great to be here. This topic is just full of assumptions, isn't it? And I think some of the research we'll look at today might surprise a few people. It certainly challenges some common ideas.
I'm already intrigued. Okay, let's set the stage. We've got three big questions we want to tackle to frame this deep dive. First up, that 10,000-hour rule. It feels like it's become gospel, hasn't it? In music, business, everywhere.
It really has, yes.
But is it truly the universal blueprint for becoming an elite athlete? Or are we perhaps missing something crucial? Are there other factors just as important, maybe more so?
That's the first big one.
Okay, second, beyond just the hours you put in, how much does your actual body, the hardware you're born with, your biology, how much does that set your athletic ceiling?
Do sports genes really exist in the way people often talk about them?
Yeah.
And how big a role do they play?
Exactly. How significant are they really? And third, we often see certain groups, maybe from specific countries or regions, dominating particular sports, sprinters from one place, marathon runners from another.
Yes, those clusters of talent.
Is that purely down to opportunity, better coaching, facilities, maybe just cultural emphasis? Or is there a deeper story there, something linked to, well, ancestry and maybe even evolution?
These are absolutely the core questions. And you're right, the simple nature versus nurture framing just doesn't cut it. It's far more intricate.
So we'll be looking at how practice really shapes perception, how the physical gifts matter.
Definitely. And how environment and genetics weave together in these really interesting ways across the globe.
Sounds brilliant. Right, let's start by taking apart this practice principle, and specifically that 10,000-hour rule. It's everywhere. Feels like a guarantee sometimes. Where did it actually originate?
Well, the idea really gained traction from the work of a Swedish psychologist, K. Anders Ericsson, back in the early 90s. He did this now famous study on violinists at a top music academy in Berlin.
Ah, yes, the violinist study.
Exactly. He found that the very best violinists, the ones considered elite, had averaged about, 7,410 hours of solitary practice by the time they were 18.
Right.
And by age 20, that number was typically hitting or passing 10,000 hours. So the conclusion drawn was, well, it looked like a straight line. More hours equals better performance. Practice seemed to be the direct cause of what people often called innate talent.
Okay, so it looked pretty clear-cut in that study. Practice makes perfect, literally.
Ericsson then sort of extrapolated from that, suggesting this wasn't just about violins, but applied across loads of fields: chess, music, even sports, citing some early work on how experts see things differently.
It's a very compelling, almost democratic idea, isn't it? Just put in the hours and you can get there. But you mentioned there were critiques of how that research was done. What was the issue?
Yes, and it's a really important critique. The main problem is that these were mostly cross-sectional and retrospective studies,
Meaning?
meaning they looked at people after they'd already become successful, like after they got into the top music academy.
Okay, so they only studied the winners, effectively.
Precisely. By only looking at the elite group, the method couldn't really account for all the people who might have practiced just as hard, maybe even harder, but never made it to that top level.
Or those who got there much faster with fewer hours.
Exactly. It's a bit like studying lottery winners and concluding that buying tickets is the only thing that matters for getting rich. You're ignoring everyone who bought tickets and didn't win. It showed a correlation in a select group, not necessarily a universal rule of cause and effect.
That makes a lot of sense. You're looking backwards at a pre-selected group. So what about tracking people forwards, longitudinal studies? That sounds like the way to really test it.
It absolutely would be the gold standard, you're right. But it's incredibly difficult to do properly. Think about someone like Dan McLaughlin.
The guy who quit his job to play golf, aiming for 10,000 hours.
That's the one. His story is fascinating, shows incredible dedication. But imagine trying to recruit hundreds of people, get them to commit years to practicing something new, track every single hour accurately.
Logistically, it sounds like a nightmare. And ethically tricky, too, maybe.
It is. So most research still ends up relying on people remembering how much they practiced, which, can be a bit unreliable. Biases creep in.
Okay, so given those challenges, what does other evidence tell us? Does the 10,000-hour rule actually hold up when you look across different sports, or more closely at the data?
Well, not really, no. Not as a universal law. The evidence against it being a magic number is pretty strong. Take chess, for instance.
Okay.
There's documented evidence of one player reaching master level in only 3,000 hours, but another player needed 23,000 hours to get to the exact same level.
Wow, that's nearly an eightfold difference.
Exactly. And perhaps even more telling, some players put in over 25,000 hours and never reached master level. So hours alone clearly aren't the whole story.
Right. It's not just quantity.
And in other sports,
Yeah.
research suggests elite status in things like basketball, field hockey, wrestling. It often averages closer to 4,000 to 6,000 hours.
Much less than 10,000.
Considerably less. And then you have cases like Vicky Wilson, the Australian netball star. Truly exceptional player. She made the national team with only about 600 hours of formal practice.
600. That's astonishing.
It is. It really drives home the point that 10,000 hours isn't always necessary, nor is it always enough. Practice is vital, absolutely, but how effective that practice is seems to vary hugely between individuals.
Okay, so it's not just the sheer volume of hours. What about those moments in sport that feel like pure instinct, lightning reflexes, incredible anticipation? Is that learned through practice too, or is that something innate?
That's a great question. And it leads us to this idea of learned perceptual expertise. It's crucial. What looks like raw speed or instinct is often actually a highly developed mental library.
A library of patterns.
Exactly, built up through thousands of hours of practice. Think back to Jenny Finch striking out Albert Pujols and Barry Bonds.
Right. Two of the best ever.
They weren't baffled because she threw incredibly fast like a baseball pitcher. They were baffled because their brains had no database for underhand softball pitches. The spin, the trajectory, the pitcher's movements, it was all alien.
So they couldn't predict it. They were just reacting at the last second.
Precisely. Their fundamental reaction speed, hitting a button when a light flashes, is probably no different to yours or mine. Around 200 milliseconds, that's pretty standard for humans.
So it's not about physically reacting faster in that basic sense. It's about seeing more, processing faster, seeing the future almost.
That's a brilliant way to put it. Researchers like Janet Starks did some fascinating work on this. She showed that elite athletes don't have faster, simple reaction times.
Okay.
But if you flash them a picture of a game situation for just 16 milliseconds, literally a blink-and-you-miss-it flash that a novice wouldn't register properly.
16 milliseconds. That's incredibly brief.
It is.
Yeah.
Yet, top volleyball players, for instance, could look at that flash and extract crucial information. They could understand the play, figure out roughly when and where the photo was taken. A novice just sees, well, nothing meaningful. It's like a chess grandmaster, seeing a position for 5 seconds and understanding vastly more than a decent club player does in 15 minutes. It's all down to that learned database of patterns and situations. This sophisticated software is built by deliberate practice.
That chess analogy really clicks. Practice isn't just repetition. It's building this incredibly complex internal library. But you can have the best software, can't you? But if the computer itself, the hardware, isn't up to the job.
Exactly. The software won't run properly, or maybe not at all. Which brings us neatly to the other side of the coin. The unavoidable reality of our innate physical hardware, our biology.
How much does that dictate what's possible for us athletically, our ceiling?
This is where we have to move beyond just talking about practice.
Okay.
That learned skill operates on a physical foundation. And some foundations are just better suited for certain tasks.
Mm.
Vision, for example. Hugely important, often underestimated.
Really? Vision specifically?
Absolutely. Louis Rosenbaum did a meticulous study on the LA Dodgers baseball team. He found their average visual acuity was about 2013. That's significantly sharper than standard 20/20 vision.
Better than perfect vision, in a sense.
Yes. And even more revealing, the major league players consistently tested better than the minor league players.
Okay, suggesting a link to performance level.
Definitely.
Ah.
The most famous story is probably Mike Piazza, the Hall of Fame catcher. He was drafted incredibly late, something like the 13,390th pick.
Wow. Why so late if he was that good?
Well, he was apparently picked almost entirely based on Rosenbaum's vision data. Someone saw those exceptional visual scores and took a massive gamble, and it paid off spectacularly.
So it's not just about seeing clearly in general, it's about specific visual skills needed for a sport.
Exactly that.
Yeah.
The U.S. Olympic softball team, for example, they tested with an average acuity of 2011, even sharper, plus outstanding depth perception and contrast sensitivity, all vital for tracking a small fastball. But archers, they need amazing static visual acuity for hitting a still target, but maybe not the same level of depth perception. Fencers, on the other hand, need brilliant depth perception for those quick, close-range judgments.
Different demands, different visual strengths.
Precisely. Even picking up the spin on a ball, like seeing the red seams on a baseball that relies on sharp vision. Your amazing mental software needs top-notch hardware, like clear vision, to get the information it needs early enough to work effectively.
Makes sense. Beyond vision, what other physical hardware traits are really significant, things we might not think about immediately?
Well, subtle biomechanics can make a huge difference. Take the Achilles tendon.
The one connecting the calf to the heel.
That's the one. Stefan Holm, the Swedish Olympic high jumper, quite short for a high jumper, actually was incredibly successful. Partly because his intense training had made his Achilles tendon unbelievably stiff.
Stiff. Is that good?
In this context, yes. It meant it acted like an incredibly powerful spring. Took enormous force to stretch it even slightly. Now, contrast him with Donald Thomas, another high jumper from the Bahamas.
Okay.
Thomas had a naturally very long Achilles tendon, over 10 inches. That length inherently gave him a massive capacity for storing and releasing elastic energy when he jumped.
So one trained for stiffness, one had natural length, but both got a powerful spring effect.
Exactly. It's called the stretch shortening cycle. Think of a kangaroo bouncing its jaw. They use their long elastic tendons to store and release energy very efficiently. A longer or stiffer tendon can store more energy and release it more explosively. It's a critical mechanical advantage, whether you build it through training like Holm or you're born with it like Thomas.
Built in or built up. Fascinating. What about muscle fibers? Fast twitch, slow twitch, we hear those terms a lot. How much is that down to genetics?
Muscle fiber type is a really fundamental piece of innate hardware. It heavily influences whether you're built more for power or endurance.
Yeah.
You basically got fast twitch fibers, type 2.
The explosive ones.
Yes, powerful, but they tire relatively quickly. They grow well with weight training. Then you have slow twitch, type I. Their endurance fibers generate less force, but keep going for ages.
And most people have a mix.
Most people have a mix, yes. But elite athletes often have a distribution heavily skewed towards what their sport demands. Elite sprinters might have 75% or more fast twitch fibers in key muscles.
For that explosive start.
Exactly. Whereas top marathon runners, like Frank Shorter was found to have, might have 80% slow twitch fibers, perfect for endurance.
Okay, so you're born with a certain distribution. Can training change your fiber type? Can you turn slow twitch into fast twitch if you train for power?
Well, this is what some people find a bit disappointing, actually. The research overwhelmingly says, no, not really. Except in very extreme, unusual circumstances, like after a major spinal cord injury, you can't fundamentally change a slow twitch fiber into a fast twitch one, or vice versa.
So you're largely stuck with the ratio you've got.
Pretty much. Training can definitely make your fast twitch fibers more resistant to fatigue, or make your slow twitch fibers stronger. You can optimize what you have, but you can't change their basic type.
And that has real implications for training, presumably.
Huge implications. There was a Danish physiologist, Jesper Andersen. He noticed that many of Denmark's naturally fastest young football players were actually dropping out due to chronic injuries.
Why was that?
Because, paradoxically, the standard intensive training programs weren't suited to their fast twitch physiology. They were getting injured. So coaches ended up perhaps unintentionally, favoring the slightly slower players who are less injury-prone on those programs. A real mismatch between innate ability and training approach.
Wow. So you need to train the athlete you have, not the athlete you wish you had? What about muscle growth itself? Are some people just genetically programmed to build muscle more easily?
Absolutely. There's strong evidence for that. The most extreme example, though rare, is the German super baby case.
I think I've heard of this.
A boy born with visibly double the normal muscle mass. Turned out he had mutations on both copies of his myostatin gene.
Myostatin, that's the gene that limits muscle growth.
Exactly. It acts like a brake. He basically had no brakes, so his muscles just kept growing.
Yeah.
Interestingly, his mother was a professional sprinter, and she had one copy of the mutant gene. Suggests a genetic link to enhanced muscle.
And we see this in animals, too.
We do. Belgian blue and Piedmontese cattle are famous for this double muscling due to natural myostatin mutations. Certain whippets have a mutation that makes them much more muscular and faster racers.
Right, faster dogs.
Even in racehorses. Thoroughbreds with a specific version of the myostatin gene, the C version, tend to be better sprinters and earn more money. Less myostatin, more muscle, more speed.
So genetics clearly plays a role in baseline muscle potential. But what about how people respond to training? If two people do the exact same workout, do they get the same results?
Not even close, usually. And this is another really crucial point that challenges the simple effort equals outcome idea. The Heritage Family Study was massive for showing this.
What did they do?
They took thousands of people who didn't exercise much, put them all in the exact same standardized aerobic exercise program.
And the results?
All over the place. Some people saw virtually zero improvement in their aerobic capacity. Others improved by over 50% from the same training.
50% difference, that's huge.
It's massive. Clearly, some people were high responders to that training and others were low responders. It strongly suggests that how much benefit you get from exercise your trainability has a significant genetic component.
And does this apply to strength training too?
It does. A study at the University of Alabama, Birmingham put people on identical weightlifting programs. Again, huge variation. Some saw basically no muscle fiber growth. Others saw a 25% increase. And then there were extreme responders who saw a 50% increase in muscle fiber size.
Wow. What made them extreme responders?
They found these individuals had significantly more satellite cells. These are cells crucial for muscle repair and growth. So again, an underlying biological difference dictating the response to the same training stimulus.
So effort is essential, but your biology dictates how much return you get on that effort.
Exactly. Think of someone like Jim Reed Jones, the American runner. He apparently started high school running as, quote, the sorriest member of the team. Really struggled initially.
Okay.
But his body responded incredibly well to the training. He improved dramatically very quickly, becoming a state champion, then world class. His baseline might have been low, like some of those heritage low responders, but his trainability was extraordinary. Not everyone, even with the same dedication, would see that kind of transformation.
That's a really powerful illustration. The same input doesn't guarantee the same output. Our biology sets the parameters. Okay, let's shift gears slightly. Let's look at how the ideal athlete's body has changed over time and then dive into those geographic hotspots of talent. We hear about this big bang of body types in sports. What does that refer to?
It refers to this really dramatic divergence in the physical shapes and sizes of elite athletes over the last century or so. Back in the early 20th century, maybe around the 1920s, the thinking was that a fairly average, all-round build was best for most sports.
One size fits all, kind of?
Sort of, yes.
Huh.
You might look at photos from, say, 1925, and an elite volleyball player and an elite discus thrower could look remarkably similar in size and shape.
Okay.
But as sports got more professional, more competitive, more scientific, well, you started seeing what you could call artificial selection at play. Bodies started becoming hyper-specialized for the specific demands of each sport.
So that average build just wasn't competitive anymore in most elite sports. Can you give some examples of this specialization?
Oh, absolutely. The differences now are often huge. Compare an average elite male shot putter today to an average elite male high jumper. The shot putter is likely about 2.5 inches taller, but a massive 130 pounds heavier.
Oh, polar opposites almost.
Pretty much. Or look at female gymnasts. Over about 30 years, their average height dropped from around 5'3" to 4'9". A smaller, lighter frame is simply more advantageous for the incredibly complex rotations and flips they perform.
That makes sense. Any other examples?
Water polo players. A study in Croatia found that elite players' arm lengths were increasing 5 times faster than the arm lengths in the general Croatian population over a couple of decades. Longer arms give a clear advantage for reaching and throwing in the pool. The successful body types are literally pulling away from each other.
And the NBA must be a prime example of selecting for a very specific, unusual body type.
Absolutely striking. The height difference alone is amazing. You take American men aged 20-40 who are genuinely 7 feet tall or more, a staggering 17% of them are currently playing in the NBA.
17%! That's incredible. 1 in 6, basically.
Roughly, yes. If you found 6 random 7-foot American men, odds are one plays pro basketball. But it's not just height, it's proportions. The ideal Vitruvian man is depicted in a square, right? Height equals arm span.
Right. Leonardo da Vinci.
Well, the average NBA player is more like a rectangle. Their average arm span to height ratio is about 1.063. So their arms are over 6% longer than they are tall.
That's a huge difference from the average of 1.1 ratio.
It is. It actually approaches the criteria for Marfan syndrome, a condition that causes long limbs. Think of players like John Wall, listed at maybe 6'3", but with a reach over 6'9". Or Chuck Hayes, 6'5", but with a 6'10" wingspan. That extra length, that innate trait, compensates massively.
It's like they're built for the job, and this specialization goes right down to the skeleton, doesn't it? How much muscle you can carry.
It does. There's fascinating work by an exercise scientist, Kevin Holloway, suggesting a general biological rule. For every kilogram of bone mass, the body can typically support a maximum of about 5 kilograms of muscle.
A 1-to-5 ratio.
Roughly. So if an Olympic thrower has a skeleton that's just, say, 6.5 pounds heavier than an average man's skeleton,
Okay.
that denser frame can naturally support over 30 pounds of additional muscle mass compared to the average person. Their skeleton dictates their muscle potential to a large extent.
And that affects training, too.
Definitely. A javelin thrower needs explosive power, but also speed, so they wouldn't want to carry much excess weight beyond that optimal muscle ratio. It would slow them down. A sumo wrestler, though, extra mass is an advantage, so they might benefit from exceeding that ratio. It shows, again, training has to be tailored to the underlying structure.
This idea of matching body type to sport sounds like talent transfer. Finding people with the right build and putting them into a sport they might not have considered. Does that actually work?
It works remarkably well sometimes. It really shows how the right hardware can shortcut the learning curve. The Australian Institute of Sport did this brilliantly.
What did they do?
They recruited athletes from surf life-saving people with incredible power, balance, nerve, often called beach babes, and they put them onto skeleton sleds.
Skeleton? The head-first ice track thing, having never done it before.
Exactly. Novices. And apparently within just 3 runs down the track, some of them were breaking Australian national records.
Wow. That's incredible. Shows the power of the right physical foundation.
Absolutely. Another great example is Elisa Camplin. She was a top gymnast and sailor, never even seen snow before she switched to aerial skiing.
Aerial skiing. That looks terrifyingly complex.
It is. Requires huge spatial awareness, power, precision. Yet she won Olympic gold. And she did it just 6 weeks after breaking both her ankles.
That's just unbelievable resilience and aptitude.
It shows that if you have the right fundamental physical attributes, the hardware gaze, you can sometimes learn the specific skills of a new sport astonishingly quickly and reach an elite level. It's about getting the best all-round athletes with the right predispositions into the sports that suit their biology.
Which kind of pushes back against the idea that you must specialize super early in one sport, doesn't it?
It really does. And there's growing evidence that early specialization might not always be the best path. In fact, it can sometimes be detrimental.
How so?
It can lead to burnout, overuse injuries, and sometimes what coaches call speed plateaus. Athletes hit a ceiling because their early training was too narrow, didn't build a broad enough athletic base.
Interesting. So maybe starting broader is better.
It seems that way for many sports. A big Danish study in 2011 found that athletes who were near elite by age 15 had actually done more specialized practice hours than the ones who eventually became truly elite.
Really? The ones who made it practice less early on.
In their specific sport, yes. It was only after 15 that the future elites really ramped up their sport-specific training. It suggested building general athleticism, trying different things when younger, what you might call late specialization, could actually be better for long-term development and reaching the highest level in many disciplines. You build a more robust, adaptable athlete first.
That makes a lot of sense. Okay, this brings us nicely to that intersection of geography, ancestry, and these talent hotspots. Like Jamaican sprinters, their dominance is undeniable. What's the story there? Is it genetics, environment, culture?
Ah, Jamaica. It's a classic and complex example.
Yeah.
There's often debate, isn't there? You have researchers like Yanis Pitsalatas who really emphasize the environmental and cultural factors, and others like Errol Morrison who give more weight to potential genetic predispositions.
And there's that warrior slave theory you sometimes hear mentioned.
Yes, that theory suggests that maybe the strongest, fittest enslaved people from West Africa were brought to particularly harsh areas like Jamaica's cockpit country, and perhaps their descendants inherited genes suited for explosive power. It's a popular idea, but, well, it's quite speculative. And genetically, Jamaicans are actually very diverse, reflecting many different West African origins. It's not one single genetic group.
Okay, so it's likely not that simple genetically. What are the stronger arguments then? What really drives that conveyor belt of sprint talent?
Well, Pitsalatas, having spent a lot of time there working with coaches, points very strongly to the environment and culture. Jamaica has this incredible champs culture, national high school track and field championships.
I've heard it's huge over there.
It's a national obsession, like the FA Cup final here, maybe even bigger relative to the population size. This creates this amazing island-wide talent identification system. Almost every kid, especially in rural areas, tries sprinting. The coaches are incredibly knowledgeable and spot talent early.
So kids with natural speed get noticed and channeled into track.
Exactly. Usain Bolt wanted to be a cricketer, but a sharp coach saw his raw speed at 14 and pushed him towards track. In other countries, a kid that big and fast might easily end up playing rugby or American football. In Jamaica, the system keeps them in sprinting.
So the culture acts like a giant sieve, catching all the fast kids.
Precisely. And it ties into this idea, you know the saying, you can't teach speed. Well, you can definitely improve technique and conditioning to make someone faster. It's also generally true that kids who are naturally slow don't suddenly become world-class sprinters as adults. Jamaica's system is just incredibly effective at finding those naturally fast kids very young and keeping them in the sport.
Okay, that makes a lot of sense. A powerful cultural and structural advantage. Now let's switch continents. East Africa, especially Kenyan runners, the Kalenjin people, their dominance in distance running feels almost mythical sometimes. Is there a similar story there? Genetics, environment?
Again, it looks very much like a combination of factors working together. The statistics are quite staggering. The Kalenjin make up only about 12% of Kenya's population, but they account for something like 3/4 of the country's top distance runners.
75% from just 12% of the people.
Exactly. And you see similar patterns with the Oromo in Ethiopia, the Sebi in Uganda. There are countless stories of people who seemed, comfortably sedentary, like a runner called Paul Rodich, who start training relatively late and just rapidly transform into elite competitors. An incredible natural aptitude.
So is there a specific physical advantage they possess?
There seems to be. Studies comparing Kalenjin boys to, say, Danish boys found the Kalenjin, on average, have significantly thinner lower legs. Maybe 15–17% thinner.
Thinner lower legs. Why does that matter?
Think of your legs swinging like a pendulum when you run. Less weight at the end of the pendulum means it takes less energy to swing it forward with every stride. It improves running economy, how efficiently you use oxygen at a given speed.
Ah, I see. Less effort required.
Precisely. And this difference seems to exist even in Kalenjin boys who aren't particularly active, suggesting it might be a more inherent morphological trait, possibly genetic.
And what about the environment? Running to school? Altitude.
Both likely play a role. Many elite East African runners did run or walk long distances to school as children. People like Derdou Tulu, Moses Kiptanui. That's thousands of hours of low-intensity aerobic work during development. But it's not universal. Paul Tergat, Wilson Kipketer, they mostly walked, so it's not the only factor. Now, altitude is fascinating and complex, too. Many train at moderate to high altitudes. But different populations adapt differently. Tibetans have that EPAS1 gene variant for better blood flow without extra red blood cells. Amhara Ethiopians seem to transfer oxygen very rapidly at the tissue level. And Ambuns increase their hemoglobin significantly.
So different strategies for coping with thin air.
Exactly. And Oromo Ethiopians are often altitude responders. Their hemoglobin increases even at moderate altitudes. Plus, being born and raised at altitude generally leads to larger lung volumes, which is a permanent advantage for oxygen intake.
It really sounds like a perfect storm of potential genetic predispositions, specific body types, environmental conditioning like altitude, and maybe childhood activity.
It does seem to be a confluence of many factors. And there was that interesting case of the American Kenyan, wasn't there?
Yes. Tell us about that.
Anthony Sandoval. He grew up at high altitude, 8,000 feet, in New Mexico, walked and ran miles as a kid, similar to some East African runners' childhoods. A top exercise physiologist, David Martin, tested him, was just blown away.
What did he find?
Described him as a physiological specimen. Long legs, big heart, big lungs, small torso, incredibly efficient oxygen transport. And Martin's conclusion was famously, you know what he is? He's a Kenyan, an American Kenyan.
Wow. So similar environmental pressures, plus maybe the right innate physiology created a similar athletic profile despite the different ancestry.
It really suggests how powerful that interplay between biology and environment can be in shaping athletic potential for endurance.
This has been absolutely illuminating. It's so clear that it's never just nature or nurture, is it? It's this incredibly complex dance between them. Okay, let's wrap up with a few quick-fire questions to nail down some key takeaways. First one. A parent's listening, they want to know if their kid has potential to be fast. What's the best, most practical genetic test they can use right now?
A stopwatch. Honestly, take them out, let them race their friends. Direct measurement of the actual skill or attribute is always better than trying to guess from indirect genetic information.
Simple, direct, makes perfect sense. Okay, next. Can anyone become truly elite if they just put in enough hours, show enough dedication, or is there a biological limit?
Realistically, no. Not everyone can become elite. As we've seen, tradability varies massively. Someone might need 8 times the practice to reach the same level as someone else. And some people, however hard they work, their biology just might not respond enough to get them to that absolute top tier. Effort is crucial, but it doesn't guarantee an elite outcome for everyone.
Right, biology sets boundaries. And final quick question, is there one single perfect athlete gene or maybe perfect genetic profile that guarantees success?
Statistically speaking, absolutely not. It's a nice idea, but the reality is far more complex. Just looking at 23 genes linked to endurance, the odds of someone having the ideal version of all of them are less than 1 in a quadrillion.
1 in a quadrillion, so basically impossible.
Pretty much, yes.
Yeah.
Most of us, genetically speaking, are somewhere in the muddled middle. Elite performance rises from a very rare combination of many favorable genes interacting, plus the right environment, the right training, immense dedication, and those crucial psychological factors too.
This has been so insightful. It hammers home that elite performance is this intricate braid. Genes lay a foundation, a predisposition.
And then environment, culture, opportunity, and crucially, the right kind of dedicated practice work to develop that potential. It's never either.
And that 10,000-hour rule. Clearly an oversimplification. Practice is vital, but its effectiveness depends hugely on the individual's biology and whether the practice itself is smart, deliberate, and personalized.
Spot on. Quantity isn't enough. Quality and suitability matter enormously.
We've also seen how specialized bodies are becoming increasingly key for elite success, with things like limb length, muscle fibers, bone structure, and sheer trainability playing huge, often genetically influenced roles.
While geography and ancestry clearly contribute to talent hotspots, we must remember the immense diversity within any population group, often more variation within than between groups.
And critically, it's not just about the physical, those psychological traits, the drive, the pain tolerance, that almost obsessive commitment.
Yes, the head stuff, often with its own genetic links too. Think of sled dogs bred for willingness to pull, or ultra runners who genuinely need that extreme activity. It's the whole package, mind and body.
Absolutely. And the encouraging thing is, even if becoming an Olympian isn't the goal, everyone benefits from exercise in their own way. Finding what works for your unique biology is key for health, enjoyment, and getting the most out of it.
That's the real journey of self-discovery, isn't it?
It really is. If you found this deep dive into athletic potential useful, please do consider rating the show or sharing it on LinkedIn or X, formerly Twitter. It really helps others find these conversations.
And perhaps a final thought to leave with. Pursuing athletic improvement at any level is really a quest to find what works for your unique biology. Taking part is a journey of discovering yourself in ways that maybe even science can't fully map yet.
A perfect place to end. Thank you so much for sharing your expertise today.
My pleasure entirely. Fascinating discussion.
Thank you for joining us on The Deep Dive. We'll be back soon with another exploration.